So let's look at the problem statement first. So the problem is that you are given an integer n and the range of this n can be less than is equal to 9 into 10 to the power 18, and it is confirmed that n can be represented as p square multiplied by q, where p and q are both prime numbers and p not is equal to q. So whatever n you have been given can be represented as p square multiplied by q, where p and q both are prime numbers and p not is equals to q. So your task is to find out the value of p and q. So let's look at some of the observations. The number one thing to be noted here that n can be represented as p square multiplied by q, right? So suppose if we have found out the q, then our p will be square root of n divided by q. But to find out this q, we need to check every prime number less than equals to n. We need to check every prime less than is equals to n, and we have to check whether that prime number divides n or not. So we have to generate all prime which are less than is equals to n, right? And the range of n is 9 into 10 to the power 18. That means we have to generate all the prime numbers less than 9 into 10 to the power 18, which will result in a time limit exceeded. So another thing we can do here is that in spite of looking for q, we can look for p, right? So n can be represented as p square multiplied by q. So we will look for p, right? And whenever we have found out a p, then our q will be n divided by p square, right? So we have to check all the prime number less than is equals to square root of n, right? So we have to check all the prime numbers less than is equals to square root of n, and if we have found such a prime number, square of which will divide n, then our q will be n divided by p square, right? So our range of n is 9 into 10 to the power 18. So square root of n is nothing but square root of 9 into 10 to the power 18, which will result in a 3 into 10 to the power 9. That means we have to generate all the prime numbers less than 3 into 10 to the power 9. So even if you do sieve of Eratosthenes or square root algorithms, you will still find that in sieve of Eratosthenes, the space complexity is of order of n. Then that means you will have to have a space complexity of 3 into 10 to the power 9, which will also result in a space limit exceeded, right? So by doing this, you also cannot solve this problem. So we have seen that by using conventional approaches, we cannot solve this problem. We have to think a little bit more and observe a little bit more to solve this problem. So the first thing to be observed here is that suppose suppose your p is less than 10 to the power 7, then the problem becomes very easy, because now you have to generate all prime less than 10 to the power 7, and you have to check whether n modulo that prime square is equals to 0 or not, right? So you have to generate all prime numbers less than 10 to the power 7, and you have to check whether n modulo that prime square is equals to less is equals to 0 or not, right? So generating all prime less than 10 to the power 7, if you want to do it using sieve, then your space complexity will be order of 10 to the power 7, which will not result in a memory limit exceeded, and you can do this. And once you have find out that p, then your q will be nothing but n divided by p square, right? So this is the case where p is less than 10 to the power 7. But if your p is greater than 10 to the power 7, that means your p square minimum will be 10 to the power 14, right? Because 10 to the power 14 is equals to 10 to the power 7 square, right? Then your maximum q will be nothing but 10 to the power 18 divided by 10 to the power 14, or we can say that order of 10 to the power 4, right? So your maximum q can be order of 10 to the power 4. Then we can say that your q will be inside 10 to the power 4. So q will be less than is equals to 10 to the power 4, 10 to the power 4, right? Order of 10 to the power 4. So if q is inside 10 to the power 4, we can also say that q must be inside 10 to the power 7, right? Order of 10 to the power 7. So in both the cases, we can see that if your p is less than 10 to the power 7, that means your p will be less than 10 to the power 7, right? But if your p is greater than 10 to the power 7, then your q will be less than 10 to the power 7. So in both the cases where p can be greater than 10 to the power 7 or less than 10 to the power 7, one of p or q will always be inside 10 to the power 7, right? So that is the most important observation for this problem. So if your p is greater than 10 to the power 7 or your p is less than 10 to the power 7, in both cases one of your p or q will always be inside 10 to the power 7, right? So we have seen that in your one of your p or q will always be inside 10 to the power 7. So then the solution is very easy. So what you have to do is you have to generate all prime less than 10 to the power 7, right? And you have to check whether that prime divides n or not. So you have to check whether that n modulo prime is equals to 0 or not, right? So suppose you have found an x, and that x divides n, right? So suppose you have found a prime number less than 10 to the power 7, which is x, and x divides n, right? So your this x can be p, or your this x can also be q, right? You don't know. Then you have to check another thing, that if x square also divides n, that means your x is equals to p. But if x square doesn't divide n, then your x is only q, right? So for this case, where x is equals to p, that means x square also divides n. That means your q will be nothing but n divided by x square. But if this is the case, that x is equal to q, that means x square doesn't divide n. That means your p will be square root of n divided by q. So generating all the prime numbers will in Sivog-Eratosthenes will require space complexity of order of 10 to the power 7, and you can do this without exceeding memory limit. And for each of the prime number, you have to check that whether that prime number divides n or not. Suppose you have found an x that divides n, that means your x can be p or your x can be q. So how to find out whether your x is p or q? You will give another check if x square divides n or not. So if x square divides n, that means your x is p, and if your x square does not divide n, that means your x is q. So if your x is p, then you will easily find out q by dividing n by x square. But if your x is q, then you can also find out p, and those two operations will require order of 1, right? So your total complexity is the total number of prime numbers present less than 10 to the power 7, and for each and every prime number you have to check whether that prime number divides n or not, and then rest of the processes. So if you like this video, please subscribe to this channel. Thank you.